Hello. In the last video we tried to motivate the idea of why we need a theory of special relativity. So we had this very surprising result from the Michelson-Morley experiment that said that however we're moving, we always seem to see light travelling at the same speed, a speed we call c. This is a really surprising result. It's very non-intuitive. It's not how everyday objects behave. If you throw a ball and then I run alongside that ball, I'm going to see it having a different speed to the speed that you measure, the person who throws it. But that's not true for light. If I try and run alongside some light, I'm still going to see the light travelling at 3 times 10 to the 8 meters per second. So this means there's no real need to create this thing called the ether. Okay, the idea of the ether was that it was some kind of background material that light travels at c relative to. But what we're saying now is that, well, light travels at c relative to everything, so what's the point of creating an ether? We also saw with the idea of the light clock, this has a very startling consequence. If we accept that everyone sees light travelling at c, then we can show that they can't always agree on the time between two events. So this is what we call time dilation. It's one of the strange effects of special relativity. In this video, we're going to start to put things on a more formal footing. We're going to describe frames of reference and how we make transformations between those frames of reference.
So the first thing we need to do is understand what a frame of reference is. From our point of view, a frame of reference is going to be a coordinate system which we use to make measurements of things from. So I'm going to draw a simple Cartesian coordinate system. So we're going to have an x-axis and a y-axis. And then let's suppose we have an event over here somewhere. So it could be an explosion. I can measure the position of that event in this frame of reference, which is really saying how far away is that event from the origin of this coordinate system. If I had a clock attached to my frame of reference, I could also measure the time that event happens. Now let's suppose I have a second frame of reference, so a second observer. They're over here, so their coordinate system has an origin in a different point in space. We need names for these frames of reference, so we're going to call this one S, and we're going to call this one S prime. And the X locations measured in S prime we're going to call X prime, and the Y locations we're going to call Y prime. And similarly, we can imagine a clock attached to this frame of reference, and when we measure the time of something, we're going to call that T prime, measured in this frame of reference. Now obviously S prime is not going to measure the same X location for this event as S. That is, X prime is not going to be equal to X because the origins of the coordinate systems are not in the same place. We can go even further. We can imagine what happens when S prime is moving. So we'll say that S prime is moving with speed u along the x-axis. So a long time ago in the past it was way over to the left somewhere. In the future it's going to be over to the right. So now, not only do these two observers not agree on the location of the event, but the extent of their disagreement is going to depend on time as well. We'd like to write down a set of equations that allows us to convert measurements made in one frame of reference to measurements made in another frame of reference. These are called transformations. In order to do this in a neat way, we need to agree some things about how we're going to set up our frames of reference. In particular, we need to agree on one special time, which we're going to call time 0. So at time 0, t equals 0, frame S prime is going to be right on top of frame S. And there must be some time when that happens, because in the past it was to the left, in the future it's to the right, so there's that one moment when it's on top of S. And we're going to call that time t0. And at that moment in time we're going to synchronise the clocks attached to both frames of reference, so that's also going to be t prime is equal to 0. And at that moment in time, and at only that moment in time, X locations measured in S are going to equal X locations measured in S prime. They are both going to agree on the location of the explosion if it happened at time 0. All other points in time, they're not going to agree. So then we can write down a transformation X prime is equal to X minus ut. So let's check this works. So first of all, let's think about the special time t equals 0. Well, when t is equal to 0, this second term is 0, we simply have that X prime is equal to X, that's what we wanted, that's what we wrote down over here. At other points in time, let's say some positive point in time, frame S prime is going to be over to the right somewhere compared to frame S. That means it's going to be closer to the event than frame S. And the distance that it's going to be closer by is how long it's been travelling since time 0, multiplied by how fast it's been travelling, so u times t. Well, that's exactly what we've got here. Okay, so X prime is going to be less than X by amount ut, which is how much closer it's got to the event. The two frames of reference aren't moving in the Y direction, so they're always going to agree on the Y location of the event. Same for the Z location coming out of the page. And then finally, providing these two clocks are good clocks, because we've synchronized them at some point, they're always going to then agree on the time of the event. T prime is equal to T. So these are what we call the Galilean transformations. They're really just the common sense, everyday transformations between measurements made by two different observers. Now, if you know a bit of calculus, you might be able to see how to go from this equation here, for x prime is equal to x minus ut, to the velocity addition rule that we wrote down in the last video. Remember that speed, v, is simply change in position with time, so dx by dt. And similarly, v prime, so a speed measured in a different frame of reference, is the rate of change of position measured in that frame of reference with time measured in that frame of reference. And since we're saying that t is equal to t prime, that's of course exactly the same as saying dx prime by dt. So what that means is, if we want to get an expression relating speeds measured in the two frames of reference, so the velocity addition equation, all we have to do is differentiate this expression with respect to time. So let's do that. So we would have dx prime by dt is equal to dx by dt minus dut by dt. Well, dx prime by dt, we've already said is v prime, so we have v prime is equal to dx by dt, v. We differentiate ut by dt, we just have u. So we have v prime equals v minus u. So that's the velocity addition formula. Now we know that the velocity addition formula does not seem to work for light. So that tells us that the Galilean transformations aren't going to work for light. So we might suspect that these equations aren't the full picture. What we'd like to do is modify these equations so that they still work for everyday objects, but they also work for light. So we're going to begin by writing down two things which we call the postulates of special relativity. So a postulate is not something that we can prove is true, but it's something that we assume is true for the point of view of developing a theory. And then what we hope is that that theory predicts things that we can then go out and measure, and if our measurements agree with our prediction, then we can say, well, that seems to be a good theory, and perhaps those were good postulates that we chose to use. So there are two postulates of special relativity. The first postulate says that the laws of physics are the same in all inertial frames, or in other words, there's no such thing as absolute motion. So this idea actually isn't a new thing in special relativity. This is a statement of the principle of relativity, and this was known about for a long time prior to Einstein. What it says is that there's no way that I can measure my absolute motion. All I can ever do is measure my relative motion compared to something else. And while this might not be immediately obvious, if you think about it for a little while, you realise that we really don't notice when we're in motion, providing our motion is constant. If we're moving at a very high speed through space, we don't feel anything. Now we might see something shooting past us in the opposite direction, but we have no way of telling whether it's us in motion or whether that object is in motion. And in fact, what the principle of relativity says is that there is no right answer to that question. All we can ever do is measure motion relative to something else. Now we use the word inertial frame of reference. Inertial means non-accelerating, because if we accelerate, we can tell that we're the ones accelerating. If you're sat in a car and you put your foot down on the pedal, you feel a force pushing you back on the seat. In that case, you're not in an inertial frame of reference, you're accelerating. And this principle no longer holds in quite the same way. The second postulate of special relativity is the experimental result from the Michelson-Morley experiment. It says that the speed of light is the same when measured in any frame of reference. Another way of saying that is that the speed of light is independent of the source of that light. And it turns out that these two postulates are all we're going to need to develop this theory of special relativity. So the first thing we're going to do is write down a new set of transformations that do work for light as well as for everyday objects. These are called the Lorentz Transformations. And they look, at first sight, not totally different from the Galilean Transformations. So we're going to have that x prime is equal to this thing which we call gamma, and we had a hint of what gamma is in the previous video, into x minus ut. So all we've really done is put this gamma in front of the x minus ut term in the Galilean transformation. Y prime is still going to be equal to y, and z prime is still going to be equal to z. Now, t prime is not going to be equal to t. So we know that we have some weird effects that go on with time in special relativity. So t prime is going to be equal to gamma into t minus ux
over c squared. We can also write these transformations the other way round. So we could write that x is equal to gamma into x prime plus ut prime. Y is equal to y prime, z is equal to z prime. And then we can have that t is equal to gamma into t prime plus ux prime over c squared. And in case you're thinking that's obvious, well, it's not. Actually, if you just try to rearrange this equation without knowing what gamma is, you can't show this. It depends on gamma being a very special thing. We'll come back to that later. In order to use these equations, of course, we need to know what this term gamma is. So gamma is equal to the square root of 1 over 1 minus u squared over c squared. So we saw this already when we did the light clock. Remember, u is the relative speed of our two frames of reference, of our s and s prime. In fact, it's the speed of s prime relative to s along the x-axis. So before we show that these equations follow from the postulates of special relativity, we're going to explore them a little bit, and in particular we're going to look at gamma. So we can make a plot of gamma. We could look at it for negative values of u and positive values of u, which really just means whether s prime is moving in one direction or the other direction. So we'll make this axis u and this axis gamma. And what we find if we were to plot out gamma is that for a value of u is equal to 0, we simply have 1 divided by 1 minus 0, which is 1 square rooted as 1. Okay, so we'd have a value here. We're going to have a problem if u becomes c, because if u is larger than c, this term here would become larger than 1, and we'd have something negative here, and we don't know how to take the square root of a negative number. We don't want to use complex numbers here. So we're going to have an asymptote at c. Okay, so at a speed c, we draw a dotted line up here, so we can't calculate gamma, it's undefined at this point. And then if we were to calculate all the intermediate points, we'd find it does something like this. So it starts off very slow, and then it suddenly begins to shoot up towards infinity, and of course never quite touching this asymptote here. And if we were to draw the line on the other side, we'd basically have a mirror image of the same thing because we have a u squared, so it's really the same as it being u. So this is what gamma looks like. For small speeds, for speeds close to 0, and by close to 0 I mean not close to c, gamma is approximately equal to 1. As our speeds approach c, gamma shoots up towards infinity. So this immediately tells us why we're not going to notice any effects of special relativity in our everyday lives. Because in our everyday lives, our speed u is very close to 0, or at least it's a lot closer to 0 than it is to the speed of light c. So when our speed is close to 0, this gamma term essentially becomes 1. So if we look at what happens to x prime, well, it would have to have x prime is equal to 1 into x minus ut, i.e. x prime is equal to x minus ut. Well, that's the everyday Galilean expression. Similarly over here, for our expression for time, this gamma will become 1, so we simply have t prime is equal to t. We'd also have this bit here, but then again, if our speed is very, very low compared to c, this term is also going to be approximately equal to 0, so we'd simply have that t prime is equal to t. So our everyday experience, we don't notice these relativistic effects because the Lorentz transformations are essentially the same as the Galilean transformations. But once our speed does become an appreciable factor of the speed of light, we're going to have a very different situation from what we might intuitively expect.
So I just wrote down these Lorentz transformations. I didn't show you where they came from. So now we're going to show they follow directly from the two postulates of special relativity. So we're going to start off by assuming some form for the transformation for position. We're going to write down that x prime is equal to something that we're going to call gamma, although we don't know what gamma is yet, into x minus ut. And similarly, the inverse transformation, x is equal to gamma into x prime plus ut prime. Now you may say, well, I've just written down the Lorentz transformation for position already. How is this a derivation? So the first thing to stress is that we don't know what gamma is yet. Gamma is some unknown. It could be that gamma is equal to 1 and then we've just got the Galilean transformations. But of course what we want to do is we want to show that gamma is equal to the Lorentz factor. You might also wonder, why must they take this form at all? Could we have something that's much more complicated with an x squared minus ut to the power of 10 or something? And there's various arguments why we can't have that. The first and simplest argument is that in the end we want these equations to reduce to the Galilean transformations for small velocities. So they must start off looking something like the Galilean transformations. We also have dimensionality considerations. We have on the left a position, So it must be that each of these terms is equal to a distance as well. So we have x there, that's fine, and of course a speed times a time gives us a distance. So there's only a small number of possibilities of what we could have here. It's also important that these transformations are linear. Okay, if we had non-linear transformations, then we would have something very strange going on. There's a principle called homogeneity, which means that we want the form of the equations to be the same wherever we are in space. And that's only going to be the case if they're linear with position. Another important consideration is isotropy, which means that the form of the law shouldn't change depending on which direction we're moving in. Now, if we think of our two coordinate systems, s and s prime, the frame we chose to call s and the frame we chose to call s prime is entirely arbitrary. So we could have chosen to call the one on the left s prime and the one on the right s. The only thing that would change is the relative direction of the motion. Okay, because in the way we set things up normally, we have s prime moving to the right with speed u. But now if we call this frame s and this frame s prime, then s prime would simply be moving to the left. So we would say it's got a speed of minus u, using the same direction for positive. So what that means is when we want the inverse transformation, all we're ever going to do is flip the sign of the speed. So this transformation here, taking us from the primes to the non-primes, has to be exactly the same as this transformation here, except everywhere we had a u here, we put in a minus u, and of course two minuses make a plus, so we've got plus ut prime here. If you want to look more into why the equations have to have this form, there's an excellent section in Wolfgang Rindler's book on special relativity. I've put a link down in the description. So we have our two general forms of the equations, and what we'd like to do now is work out what gamma is. And to do that, we're going to use the second postulate of special relativity. So I've drawn here two frames of reference, s and s prime, and I've drawn in the x-axis x and x prime. And what we're going to do is we're going to have a pulse of light that starts at the origin of s and moves to the right with speed c. Don't forget, as always, the frame s prime is moving at speed u relative to s. Now, to simplify things, what we're going to say is that the pulse of light starts at the origin of frame s at time 0. So at time 0, which is equal to the time 0 measured in this frame of reference, because remember that's always how we set up our frames of reference. So we've got t equals t prime equals 0, and at that point in time, the position of the pulse of light is 0 as measured in s, and it's also going to be 0 as measured in s prime. Because again, remember that special time, t equals t prime is 0, is when the two frames of reference are on top of each other. So for that one instant in time, they both measure the same position for the pulse of light. At any other point in time, they're going to measure a different position for the pulse of light. So in frame s, we're going to have that the position of the pulse of light, x, is given by its speed multiplied by how long it's been moving for, so c times t. Similarly, in s prime, we're going to have that x prime is equal to c times t prime. So in this frame of reference, its position is its speed multiplied by how long it's been travelling for as measured in this frame of reference. So what we're going to do is we're going to take these two equations, which have encoded the idea that both observers see light travelling at c, and we're going to substitute those into our general transformations. So first, into the x prime transformation, we're going to have that x prime equals ct prime, and that's equal to gamma into x, which is ct, minus ut. And then I can simplify things a little bit, so I can say that ct prime is equal to gamma t into c minus u. Okay, now substituting into the second transformation, the inverse transformation, we're going to have that x is equal to ct, so we've got ct is equal to gamma into x prime, which is ct prime, plus ut prime. And again, I'm going to simplify things a little bit. I'm going to group the t primes. I'm also going to divide both sides by c. So we're going to have t is equal to gamma into c plus u t prime over c. I can then substitute this equation into this equation here. So we'll have that ct prime is equal to gamma, then t comes from here. So we have another gamma into c plus u over c, t prime, and then we've got c minus u. So this looks a bit messy, but actually we can do a lot of simplification. We can get rid of the t primes from both sides. We can get rid of the c and make that a c squared up here. And of course we're going to have a gamma times a gamma, which makes a gamma squared. So rearranging, we're going to have that gamma squared is equal to the square root of c squared over c squared minus u squared, where I've also taken the fact that if you take c plus u multiplied by c minus u, if you multiply that out, you get c squared minus u squared. And then, of course, I can take the square root of both sides. I can also divide top and bottom by c squared here. So that's going to give me that gamma is equal to the square root of 1 over 1 minus u squared over c squared. So we've done it. We've shown that gamma is equal to the Lorentz factor that we wrote down previously. And what's really critical to understand is that although we've assumed a general form of the transformations, the fact that gamma is equal to this follows directly from the second postulate of special relativity, the idea that both of these observers see the pulse of light moving at the same speed, c. You could then go on to work out what the transformation for time is by playing around with these equations. I'll leave that as an exercise and ask in the comments if you're not sure how to do that. So now we've really made some progress. We've written down the Lorentz transformations that allow us to transform measurements made in two different frames of reference correctly in special relativity. Not only have we written them down, but we've actually shown that they follow directly from the postulates of special relativity, particularly the idea that all observers see the same speed for light, regardless of how they're moving around. In the next video, we're going to start to explore one of the most interesting consequences of these equations, the effect we call time dilation. So please don't forget to subscribe, and I'll see you next time.